All right, so the other day when we were in class, we were talking about a variety of topics. So quite a bit of math. You probably want a notepad and a calculator handy just to play around a little bit with this. There are going to be a lot of new terms. First, let's talk about measuring distance to stars using the phenomena called parallax. Parallax was an ancient methodology that people like Tycho Brahe and Kepler and Copernicus and even Galileo tried to make work, but they didn't have the technology at the time. In fact, we barely have the technology now to do a really good job of it, though I'm sure some professional astronomers would complain about that statement. If we look at our solar system, you have the sun in the center and the Earth orbiting here. The Earth obviously sweeps out locations in the course of the year. So in 6 months' time, at E1, the Earth may be looking at an object in deep space, and that object is out there someplace. It appears to be over here in the sky. And then 6 months later, looking at the same object, it may appear to be over there in the sky relative to very distant objects. But what's happening is as the Earth goes back and forth in its orbit, the object seems to wobble relative to further distant background stars. And that allows us to do some very simplistic trigonometry to figure out how far away that object is away from the solar system. What's really interesting about this is that these angles are tiny. This angle here, we'll call P, is the parallax angle. It is so tiny, it's typically measured in milli-arcseconds. And as a review, 1 degree equals 60 arc minutes, which equals 3,600 arc seconds. So every arc second is 1/3600th of a degree, but we're measuring these in milli-arc seconds, which is yet 1/1000th, even smaller. The cool thing is that this distance here and this distance here are pretty much the same because the parallax angle is so small. The math, therefore, becomes a very close small angle approximation where the distance in parsecs equals 1 divided by P, which is measured in arc seconds. If that is measured in milli-arc seconds, then you'd have 1 divided by P, which is then divided by 1,000, or just simply 1,000 divided by P. The answer is in units of parsecs, and 1 parsec, abbreviated PC, equals about 3.26 light years. So that's pretty much the way that astronomers first started measuring distance to things in outer space. It's the most simplistic method. It requires high magnification, big telescopes, and a lot of time. Obviously, we have to wait until the Earth goes around in its orbit. But it is effective. We're talking about measuring the brightness to things. This guy back in about 120 BC named Hipparchus in Greece was a pretty good proto-scientist is a good way to look at it. He looked up at the sky and decided that it would be a good idea to label the stars by their apparent brightness. And thus was born the apparent magnitude system. And the apparent magnitude system, we're always going to give apparent magnitudes in lowercase m. He started with the brightest object in his sky at the time, Vega, the star Vega, and he called it 0. And then he worked his way out to +6 for the faintest things that the eye can see. So this is going to catch you a little bit by surprise. The faint things are positive values, and the bright things are typically negative values. For example, the telescopes here at Phillips Exeter Academy can see out to about magnitude 18, while the largest telescopes, like the Keck telescopes in Hawaii, can get out to about magnitude 30. It's pretty faint. Things like the moon are about magnitude 11 when it's full, and -11, and the sun is about -26. Very bright. The mathematical relationship here, of course, was created by Hipparchus's eyeball, and it wasn't until the mid-19th century that people decided that they really needed a better mathematical way to break this down, be a little bit more scientific. They decided that a range of 5 magnitudes would be equivalent to a brightness increase of about 100 times. And then they decided that would be the way to go, so they made it precisely 100 times. And since it's a logarithmic scale, the math looks something like this, where the intensity of an object, let's call it A, in ratio to the intensity of object B equals 2.512 to the power of their apparent magnitude difference. So what you see here, 2.512 is the 5th root of 100. And they're using the apparent magnitude difference to give you an apparent intensity ratio between the two. So if you wanted to calculate how much brighter the moon is than Vega, you'd take, you'd consider the moon intensity A, Vega intensity B, and you'd set that equal to 2.512 equals the magnitude of Vega, which is 0, minus the magnitude of the moon, which is negative 11. So it would be 2.512 to the 11th power, and you'd see just how many times brighter the full moon is than the star Vega in our sky. And note that this is all relative to our position here on Earth. This has absolutely nothing to do with the true brightness of an object. We know that the moon doesn't give off its own light, and it's reflecting light. Vega, a star, does make its own light, and is, trust me, considerably more luminous than the moon, but it is considerably more far away as well. To take this into account, astronomers then created the next system called the absolute magnitude system. And absolute magnitudes are always denoted with a capital M. So what astronomers did was they took that number line once again, and they placed all the objects of known luminosity on the number line such that we would be looking at them at a mythical distance of 10 parsecs. So everything here is seen as if it were at a distance of 10 parsecs. And it turns out that the sun is really not all that bright at 10 parsecs. At positive 5, we have the sun. Vega is just a little bit above 0. For example, Betelgeuse is way over here someplace in the negatives. And still, things that are really luminous will have smaller values. Really luminous. High luminosity. And over here, not so luminous over there on the right-hand side. And the math is still appropriate. You can say that the intensity of A and intensity of B equals 2.512 to the power of the absolute magnitude difference. But you can also take this a step further and say, hey, this is about actual luminosity comparison. You can say that the luminosity of A to the luminosity of B equals 2.512 to the magnitude difference. But you can also say that luminosity A, since you know the equation, 4 pi r squared, sigma t to the 4th of object A relative to the 4 pi r squared, sigma t to the 4th of object B is now true. And that gives you a pretty magnificent way of determining things. If you take the spectra of your objects and you know their absolute magnitudes, then you can tell me their radii, which is a really neat statement. And at this point, you also have a hint that there's a relationship between absolute magnitude, apparent magnitude, and distance. So here's the last equation. It turns out that the apparent magnitude minus the absolute magnitude of an object is going to equal negative 5 plus 5 times the log to the base 10 of the distance to that object in parsecs. So let's play with this just a little bit to confirm what we're thinking. If the object that we're applying this equation to is 10 parsecs away, that would mean that its apparent magnitude and absolute magnitude are the same, by definition. The log of 10 parsecs is 1. 1 times 5 is 5, and 5 minus 5 is 0. So that confirms what's going on here. It's kind of neat. So now you have all these equations, you have an understanding of apparent magnitude and absolute magnitude, and you also have knowledge of parallax angles and parsecs. This is the most fundamental astrophysics upon which very much, if not all, future astrophysics depends. And we'll talk a little bit more about that. See you in class.